We're going to continue our discussion of chemical bonding, this chapter, chapter 10, and specifically we're going to talk about molecular shapes. As shown in this image right below the title of the chapter, the image with the blue, black, white, and red balls, this is the structure of caffeine. In this structure, you will see at least two different types of molecular geometries associated with the different atoms in this molecule. Molecular geometry, the angles associated in chemical molecules, is based on valence shell electron pair repulsion theory. It's a long title, often abbreviated VSEPR or VESPR. VESPR theory tells us that molecular geometries can be predicted based on the number of electron groups attached to the central atom of the molecule. Or if you have a large molecule, it's a central atom of any 3 points of that molecule in which you can have an angle formed. So the most important part of determining the geometry is to minimize the repulsive actions, the repulsive forces between electron pairs. This is why it's called electron pair repulsion theory. Electrons will repel against other electrons to the extent that they move to a more stable position. The geometry is a result of that. It reflects an arrangement that favors minimum amounts of electron repulsion. In the previous chapter, we learned how to draw Lewis structures. VESPR theory is based on accurate Lewis structures. It predicts the number of valence electron pairs around the central atom. Each lone pair around the central atom constitutes one electron group, and each bond constitutes one electron group, where that bond is a single bond, a double bond, or a triple bond. Look at the example in the bottom right-hand corner. That's the Lewis structure image of ammonia. You have 3 bonding areas and 1 non-bonding area, the lone pair at the bottom of nitrogen. So you have a total of 4 areas of electron density that will generate the overall geometry of this particular molecule. All 4 of those areas, the bonded and the non-bonding areas, a total of 4, all 4 will repel against each other to create a geometry associated with that molecule. VESPR theory predicts geometries based on the number of electron groups attached to the central atom. The arrangement attached to the central atom minimizes the relative repulsion between electron pairs. Now let's take that example from the previous slide, ammonia, NH3. It has 3 areas of electrons for the bonds attached from the nitrogen to each of the hydrogens. It has a 4th area of electron density associated with the lone pair. These are not equal areas of density. It turns out that the lone pair repulsive forces are slightly greater than those in the bonded pairs because they are not being shared by the 2 nuclei of the atoms on each end of the bond. Thus, we have Lewis structures and VESPR theory that predict electron pair geometry around the central atom based on how many areas of electron density there are. In the case of ammonia, there are 4. Its molecular geometry, as shown in the image on the bottom right, is going to be slightly different. In fact, I think it's best way to describe it is more precise. The electron pair geometry is good at approximating the geometry, and then its molecular geometry gives it a more precise geometric description because it takes into account that the areas of electron density are slightly different from lone pairs to bonded pairs. There are 5 types or families of arrangements around a central atom based on the atoms and the lone pairs, bonded pairs, or lone pairs. The 5 different types are the following: linear, which is the result of 2 areas of electron density; trigonal planar, So results of 3. Tetrahedral having 4. Trigonal bipyramidal is 5. And octahedral is 6. So those are the broad families associated with the areas of electron density around the central atom, no matter what kind of densities they are, whether they're from lone pairs or single or double or triple bonds. If we want to get a more refined geometric structure, a molecular geometric structure that takes into account the different types of electron density, we can. And we'll talk about those differences in just a minute. So let's talk about the 5 different families, first beginning with the number 2 equal to the number of electron areas of density around the central atom. That's called a linear geometry. You have 2 electron groups attached to the central atom. The bond angles, as you can see in both examples, are 180 degrees. Let's look at these 2 molecules. BeCl2, this is the only possible Lewis structure, as beryllium's an exception to the octet rule. It is satisfied with just 2 electrons, each shared with the electrons around the chlorine atoms. So it only has 2 different, not different, they're 2 of the same types of electron areas of density. So therefore, those electrons will repel in such a way they go far apart as possible. The angle is between those 3 atoms is 180 degrees. Similarly, that exists with the molecule CO2. Although those are double bonds, they still represent only one area of electrons between the carbon and the oxygen on each side. So there's no more electrons, no more lone pairs. These double bonds will repel against each other, and the result they will go as far apart to minimize the electron repulsive forces, which means they'll have 180 degrees. The next family we want to discuss is the one that is called trigonal planar, that results from molecules that have 3 areas of electron density around the central atom. Let's first describe the electron density, electron pair density. If you have the molecule on the left, Bf3, boron is also an exception to the octet rule. It is satisfied with just 246 electrons around the central atom. So there's no other electron areas of density around the boron atom, so there's only 3. The electrons that in the bond between boron and each of the fluorine atoms will repel against each other to the extent that they go as far apart as possible to minimize the repulsion forces, thus forming a trigonal planar geometry equal to 120 degrees. Another example having angles of 120 degrees in terms of their electron pair geometry is formaldehyde that has the formula CH2O. The correct Lewis structure is shown on the right there. You have 3 areas of electron density around the central atom, although they're different. Because they are slightly different, the one in the area in which is described by the double bond will have a slightly greater repulsive force than the area of density between the carbon and hydrogen atoms. This is why the molecular shape of this molecule is slightly different. So again, formaldehyde, CH2O, has an electron pair geometry the same as Bf3 on the left, trigonal planar, but because the areas of density around the central atom are slightly different, you have a single bond and a double bond, the repulsive forces are greater with a double bond. It sort of pushes down on the angles, which is why you have slightly greater than 120 degrees between the oxygen, carbon, and hydrogen on both sides of the molecule, and slightly less than 120 degrees between the hydrogen, carbon, hydrogen angle at the bottom. The tetrahedral geometry is the one that's based on 4 areas of electron density around the central atom. You may recall that first slide that we talked about, there was a structure of caffeine. There are a number of parts of that molecule that had tetrahedral geometries. They're all due to the fact that there were 4 areas of electron density around the central atom. Look at the simplest example on the far left. That's methane, CH4. In 3 dimensions, each of those carbon, hydrogen, carbon angles will have 109.5 degrees angles. This is called tetrahedral geometry. And in this particular example, because each of those areas of density are exactly the same, they're all single bonded from carbon to hydrogen, then the electron pair geometry is exactly the same as the molecular geometry. In this case, they're exactly the same because there's no difference between each of the 4 areas of electron density around the central atom. The 5th group of electron pair geometry is called trigonal bipyramidal. It has 5 electron groups attached to the central atom. 2 of these electrons are what are called axial position, axial terminal atoms, as shown in the image in the blue and green on the left. And the ones in the plane are called equatorial chlorine atoms. So you have 3 atoms of the 5 that are bonded in what looks like a trigonal planar position, and then 2 top and bottom, the axial ones, in what looks like a linear position, the sum of which is called trigonal bipyramidal. You have 2 different angles associated with this, 90 degrees between the axial and the equatorial atoms, and 120 around the planar positions in the equatorial. And the last group of electron pair geometries is described by central atoms that have 6 areas of electron density around it, and that's called octahedral. SF6 is an example of this. In this example, you have axial and equatorial atoms, but they're all the same angle, so they are all equivalent in terms of their angles. So this is a very symmetrical molecule, and we do not typically describe the ones between those different positions because they're all the same. They all have angles of 90 degrees between any SFF angle. Recall from the previous chapter on Lewis structures that we're able to increase stability energy-wise if we can draw resonance structures of various molecules. In the example in this slide, you see the polyatomic nitrate, NO3 with 1 minus. The Lewis structures look like those on the bottom, 3 different ones that the result of which is a hybrid of all 3. And as it turns out, and this can be proven experimentally, even though you have different, it looks like in the top figure, you have different areas of electron geometry, electron density around the central atom, that is. You have 1 double bond and 2 single bonds. The hybrid version of that would create one that has all about 1 and 1/3 of bonds if you were to add them up and produce the average. So it turns out the electron geometry of this particular molecule is trigonal planar, based on the fact that you have 3 areas of electron density, but the molecular geometry is also trigonal planar because the resulting bonds are not different, they're the same. They all represent about 1 1/3 based on the fact that there's 3 resonance structures. So again, it's important to note that oftentimes a molecule has the same electron pair geometry as it does actual molecular geometry, as is the case with CH4. But many times the electron pair geometry and molecular geometry are different, and they're different because the areas of density around the central atom are slightly different. Single bonds, double bonds, triple bonds, or lone pairs. As shown in the example in the bottom right, that's ammonia, NH3. It has bonds between the nitrogen and hydrogen to form 3 areas of electron density, but the 4th area of electron density is lone pair. So while it has a electron pair density geometry of tetrahedral, its actual geometry is described differently. And with ammonia, you can see that the lone pair causes a greater repulsive force towards the other electron pairs that are being shared. And instead of having 109.5 degree angles, which is the ideal tetrahedral geometry, those angles between the H and H's are all 107 degrees. Let's continue to talk about the differences between electron pair geometries and actual molecular geometries. And they're largely due to distortions caused by lone pairs. Lone pairs require more space, and the need for more space causes it to create a stronger force toward bonding pairs. The size of the atom is also a factor. The types of groups are factors, single versus multiple. And what does this affect? The molecular geometry. The molecular geometry will vary. The shape will be a derivative of one of the basic ones. Let's look at these three similar geometries in these three different molecules below. They all have 4 areas of electron density around the central atom. Not shown in NH3 ammonia is the 1 lone pair on the central atom, and not shown in water are the 2 lone pairs. They all have 4, so their electron pair geometry is tetrahedral for all 3 of these molecules. However, due to the lone pairs, you have no lone pairs on the methane, you have 1 on ammonia, and you have 2 on water. The result is these lone pairs create a slightly greater repulsive force, and the angles of the ammonia atom, for example, resulting from the 1 lone pair is not tetrahedral, not exactly tetrahedral, 109.5, it's 107. Water is pushed even further because the 2 lone pairs in the central atom, instead of 109.5, it's 104.5. Again, the molecular geometries are not so perfect because they're influenced by the different types of pairs of electrons in central atoms. Bond length is influenced by the size of the atom in the bond, the number of electrons between the atoms bonds, and if you have multiple bonds. Electronegativity of the atoms forming the bond affects the geometry slightly, and the type of intramolecular bond is as well, metallic versus ionic versus covalent. Because the bonds are not identical, the observed angles are often slightly different from the ideal, and the best way to really determine the true angles is through experimentation. Once again, looking at ammonia, you can see the effect of the lone pairs on the molecular structure. The electron geometry is tetrahedral. The molecular geometry is slightly different. It's called trigonal pyramidal. Now, on the next 2 slides, you'll see a very useful table that summarizes the differences of electron pair and molecular geometries. Okay, on the first slide here, you'll see those examples that have electron groups of 2, 3, or 4. That means the number of areas of density around the central atom are either 2, 3, or 4. Remember, area of density can be a single bond, double bond, a triple bond, or a lone pair. Linear molecules that have electron groups of 2, where you have 2 bonding groups, and of course no lone pairs. The electron geometry and molecular geometry are exactly the same. The angles are 180 degrees. If you have 3 electron groups around the central atom, the electron density, electron pair geometry will always be trigonal planar. If one has 3 and no lone pairs, the molecular geometry is also trigonal planar. But if you have a lone pair with 2 bonding areas, the molecular geometry is slightly different from the trigonal planar electron geometry, and it's at an angle slightly less than 120, as we showed in the previous examples. All right, with 4 areas of electron groups or areas of electron density. The electron geometry is always tetrahedral. Molecular geometry is always going to be tetrahedral as well because you have no lone pairs. But if you have one lone pair, it becomes trigonal pyramidal. If you have two lone pairs, such as an example of water, water has two bonded pairs to hydrogens and two lone pairs, that molecular geometry is called bent. And in this next slide, you see the molecules and the geometries having 5 and 6 areas around the central atom. They have 5 areas. They will all have trigonal bipyramidal electron pair geometries. And if there's no lone pairs, it will have a molecular geometry shape of trigonal bipyramidal as well. You see the names associated with those having 1, 2, and 3 lone pairs, seesaw, T-shaped, and linear. Those are slight deviations of the trigonal bipyramidal geometry. And in the bottom half, you see those with 6 groups of electrons, or 6 areas of electron around the central atom. And they're all called octahedral in terms of their electron pair geometry. They have 8 sides, hence the name octa. And if they have none of those areas or lone pairs, then the molecular geometry will be exactly the same as the electron pair geometry, octahedral. If you have one lone pair, it's called square pyramidal. That's a slight deviation from octahedral. And if you have 2 lone pairs, you have square planar, which is another slight deviation. Now that we understand the basics of the geometries associated with molecules having central atom geometries of 2, 3, 4, 5, and 6 areas, we can describe the geometries of larger molecules, some that even have more than one different type of geometries. Let's take a biological molecule like glycine, the simplest of the amino acids. Looking at the structure on the left, you have 4 interior atoms, or I would call them 4 central atoms as well. And they each have different geometries, don't they? Some have lone pairs on their central atoms, the interior atoms, and some do not. So some have electron density geometries, electron pair geometries that are exactly the same as their molecular geometries, and others do not because they have lone pairs associated with them. As it turns out, nitrogen on the left has a trigonal pyramidal a molecular shaped geometry. It has a trigonal planar electron pair geometry. The second carbon, the first carbon going from left to right, has a tetrahedral electron pair geometry and a tetrahedral molecular shaped geometry. The second carbon going from left to right has 1, 2, 3. It's a trigonal planar geometry, electron pair geometry, and a trigonal planar molecular shaped geometry. And the fourth is like the water molecule. It has 2 oxygen atoms, it has two lone pairs and 2 bonds, one to the carbon and one to the hydrogen. It's going to be described as a bent geometry, molecular geometry. Tetrahedral based on electron pair, but bent based on its molecular shape, which is slightly different. So 4 different geometries in the 4 central atoms associated with the very simplest of the amino acids, glycine. In this next slide, we're going to talk about how you represent 3-dimensional shapes on a 2-dimensional surface. How do we do this on paper? What we do is we use put the central atom in the plane of the paper. We have straight lines that form bonds in the plane of the area. We have a hatched wedge that shows a bond going into the plane. That's like going into the whiteboard if I was doing this in class. Or a solid wedge represents a bond coming out of the plane, coming away from the whiteboard, again, if I'm doing this in class. Let's see some examples on the next slide. In this slide, we have 3-dimensional representations on 2-dimensional media. So let's start at the upper left-hand corner. A linear molecule like CO2 we can represent as being in the plane of the slide. are in the plane of a whiteboard or a piece of paper. Let's go right below it and show the tetrahedral molecule. You can put 3 of the atoms in the plane of the board, or in this case the slide. The X on the left, the central atom A, and the X on the bottom left. Those can be represented as being in the same plane. And then you have the third of the fourth atoms going into the board. That's the hatched line. That's the one represented by the X in the upper right. And then the X in the bottom right has the bold wedge that represents an atom coming out of the plane. And the others are similar examples using the same types of representations. Hatched wedges going into the plane and coming out of the plane. So let's review those key definitions and rules for predicting electron pair geometry and molecular geometry. Often the same, but most often slightly different from one to the other. So first you need to identify the central atom, draw the correct Lewis structure. Then you determine how the atoms are paired and if there's lone pairs on the central atom. You count the number of areas of electron density, and that determines its electron pair geometry. Now, if it has lone pairs, then you know that you will have slightly different molecular geometries. So, let's determine the geometry. First, the electron pair geometry, the family group, is determined by the total number of areas of bonds to the central atom. That means those with bonds and those with lone pairs. The molecular geometry dictates molecular geometry associated with a certain geometric grouping. It's all based on whether you have different types of electron areas of density, be it single bonds, double bonds, triple bonds, or lone pairs, and our lone pairs. So let's do a couple examples. You might want to try it yourself on paper, stop the video, refer to the charts in the previous slides that depict all the different geometries, be it molecular geometry or electron pair geometry. Let's start with the ammonia molecule. And here's the answer. The Lewis structure is shown at the top. You have 1 lone pair and 3 bonded pairs. So even though they're different, you have 1, 2, 3, 4 total areas of electron density around the central atom. So the electron pair geometry is tetrahedral. Now all those areas are not equal, so the molecular geometry would be slightly different. In this case, if you have 1 lone pair and 3 bonded pairs, you have what's called a trigonal pyramidal. The angles would be slightly different than that of a true tetrahedral. Let's try another one with this molecule ICl4 with the overall -1 charge. Take a second to pause the video and see if you can come up with the correct geometries yourself. And here's the answer. It turns out the Lewis structure shown to the right in brackets has 6 areas of electron density around the central atom, iodine. Now remember, you can have expanded octets as exceptions to the octet rule because you have to use all the valence electrons. In this case, the only way you can use it is to put 8 around each of the chlorines, but to have 12 around the iodine atom. So the central atom has 1, 2, 3, 4 bonds and 2 pairs of lone pairs. So it has 6 total, for which it will have an electron pair geometry of octahedral. But because it has 2 lone pairs, the molecular shape is not going to be octahedral. It's going to have 4 plus 2, 4 bonding pairs of electrons plus 2 lone pairs. That's called square planar. Now let's try to come up with the electron pair geometries and molecular shape geometries for BF3. Remember, boron's also an exception to the octet rule. It's not an expanded octet. It forms fewer. It's satisfied with 6 electrons around the central atom. And here's the answer to the BF3 molecule. The BF3 Lewis structure looks like that in the upper right. You have single bonds to each of the boron fluorine atoms. Thus, the electron pair geometry is exactly the same as the molecular shape geometry because there's no lone pairs. All three of the bonding areas around the central atom, boron, are equal. So the geometries will be exactly the same. Next, let's talk a little bit about polarity and its relationship to geometries. We know what polarity is. We've discussed this in the earlier chapters. It's a difference in electronegativity from one side of a bond between two atoms to the other side. So why are some molecules polar and others are not, nonpolar? In order for this to occur, then you must have polar covalent bonds within the molecule. Or the molecule must have a net dipole that is not symmetrical. You can have polar bonds in the molecule, and if you have multiple polar bonds, they may cancel each other out so that the net dipole is nonpolar. Let's show some examples. Here is an example of a a nonpolar molecule having polar bonds. Just look at one of the double bonds here. Let's look at the red oxygen atom and its double bond to the carbon. You see the dipole arrow below pointing toward the oxygen indicates that the electronegativity of the oxygen is greater than that of carbon, which means it has more electron affinity. It's pulling those electrons toward the nucleus of the oxygen away from the carbon. Now you also have that same dipole going the other direction. So you have dipole molecules, dipole moments that exist in this molecule, but they cancel out. You see how the net dipole is the sum of those two. When you add dipoles, you need to include position. So the vector addition of those two dipoles is a neutral molecule. So while CO2 has two double bonds that are polar, the net dipole is zero, so it is described as nonpolar. Another molecule shown below, of like water, also has two dipoles between each of the two hydrogen-oxygen bonds, but they do not cancel out. You have if you were to apply this in vector math, the directions do not cancel. You have a net dipole greater than zero. This is a polar molecule. So again, CO2, you have polar bonds, but the net dipole is zero. There's no dipole. That's a nonpolar molecule. Water is polar because even though you have polar bonds going in the opposite directions, they do not cancel out. The positions are important. This is why the structural understanding is important to help us determine polarity. This slide is sort of a summation of the ways to determine net polarity. The first one in the upper left sort of depicts the one with CO2, where you have a polar bond to the left canceled out by a polar bond to the right in the same direction, making the overall molecule nonpolar. The one to the next to the right, the upper right, is similar to that in water. You have polarity that does have a direction, and there's others shown here with 3 and 4 different types of polarity, and a net polarity is shown.